Today I want to tell you the story about Ira Remsen. Ira was a college student in the 1800s, and he was reading his chemistry textbook one day, studying for a test, when he read the statement, "Nitric acid acts upon copper." Well, he had no clue what that meant, and so he's trying to figure out, how am I going to figure this out? And reaches into his pocket, and he finds 2 copper cents. And so I've got 2 pre-1982 pennies here, and they're pre-1982 because prior to 1982, pennies were pure copper. Since then, they're a mixture of copper and zinc, so I have to use the older pennies. And I've got a bottle of nitric acid here. Ira found a bottle of nitric acid. I have no idea where he found it, but he had one. So I'm going to take the nitric acid and add it to the pennies, and we're going to do the same experiment that Ira did. And let's see what happens. So let's stopper this. Add the nitric acid. Give it a little swirl. And right away you see the same thing that Ira saw. The solution turns this beautiful green color, and it's bubbling. And as you look, you can see there's even more green. And as this continues to react, Ira notices there's this really noxious reddish-brown gas. And we can see it too. It's starting to fill our container completely. Now, Ira's watching all this. He's starting to understand. Now I get it. Nitric acid acts upon copper. Well, the way we've got this set up, if you look over to my right here, you're going to see that it's bubbling over on the other side because all of that gas that we're producing is coming through the round flask and over to this beaker on the other side. And we've colorized this with a little pink solution, and keep an eye on it and see what happens. So let me keep telling you what Ira's seeing. Ira keeps watching this, and as he's starting to go, he's understanding more and more what it means that nitric acid acts upon copper. But as he's watching, he's noticing that his pennies are starting to disappear. While I'm thinking of it, take a look over on my right here, and you'll notice again that pink color that was in there is now gone. And if you look closely, you'll see that there's still reddish-brown gas that's bubbling through the tubing. So let's go back to Ira's story, and we're going to let this go for a little bit because it takes a few minutes. Ira's reading all this, and he's saying, wow, and he looks in and he says his 2 copper cents are starting to disappear. They're dissolving in the nitric acid. So he said, wait a second, I need those pennies. That's my beverage money for the weekend. So he reached in and he grabbed those 2 copper cents, and then he learned his second lesson. Nitric acid acts upon fingers. So he took his 2 copper cents and he threw them out the open window, and he wiped his hands on his pants. And he learned his third lesson. Nitric acid acts upon pants. Now, Ira went on to become a graduate in chemistry and get his PhD in chemistry, and ultimately became the president of Johns Hopkins University. In addition, he did a lot of things beyond that to affect how we train graduate students in the physical sciences here in the United States. And he was the first recipient of the Priestley Medal from the American Chemical Society in the early 1920s. Now, Ira wrote his memoirs, which is where this story comes from, and he describes this one simple experiment as being the most important experiment he ever did in his career. Part of the reason I'm doing it here for you today is because this is a perfect example of an entire year's worth of introductory chemistry. First of all, we've got nitric acid. We're adding acid to a solid. That solid's dissolving. Whenever a solid dissolves like that, if it's a metal that's dissolving, you've got an oxidation-reduction reaction going on. The metal is being oxidized to an ionic form, and the HNO3, the nitric acid, is being reduced, and we make this NO2 gas. One of the other things that we notice when we do this is if I put my hands on here, this beaker is very warm. This is an exothermic reaction, so there's a little bit of thermodynamics going on here as well. Now, I want you to keep an eye over on my right-hand side here again, because there's more that's going to be happening over here. So I'm going to keep talking about some of the other things going on. So we've got an oxidation-reduction reaction. We've got this NO2 gas. Remember that NO3 became NO2, so it lost an oxygen. It was reduced. NO2 has an odd number of electrons. When you draw the dot picture for NO2, you're going to find out there's a leftover electron. Anytime there's that odd number of electrons, you end up with a compound that has a dark color like this, a very visible dark color. In fact, that NO2 gas is the main component of smog. So if you look at the clouds over LA on a bad day, you'll see this reddish brown clouds over there. So now we've got electron dot pictures, we've got exothermic reactions, we've got oxidation reduction. We obviously produced a gas, and so we've got gas laws happening over here. And then look back at this big beaker and remember what it started. It started pink, and it turned color because as the NO2 dissolved in the pink solution, I had tinted it pink with some base. We were able to neutralize that base. Now, if you look carefully, you'll see that the tubing over there is now turning colorless, and that reddish-brown color that was in the tubing is disappearing. It's moving backwards. As this reaction cools off, remember, it generated a lot of heat. Now it's going to cool off, and as it cools off, the pressure on this side is going to be much higher. So if we look real closely in here, we're going to be able to, very soon here, we're going to see that this gas over here, the pressure on this side, pushing through here. And inside here, we're going to see it's going to come over at about, there we go, here it comes. You can see that as the liquid comes over and it starts to mix with the solution over here, we're going to see a completely different color change. And what we see now is a blue color. Now remember, the only things that are in here are nitric acid and copper. So why did it start green and why did it end blue? That's our last question for you for today. And the reason it does that is before, when we started, it was copper metal in an anhydrous or without water solution of nitric acid, and we saw copper ions that were green, they were without water. And now as we added water to this, we get this brilliant blue color, which is aqueous copper ions. And these aqueous copper ions, you can see these. If you go look at a copper-colored roof on a dry day, what color is it? Hopefully you said to yourself, hey, it's green. I challenge you, go out and look at a copper-colored roof in the middle of a rainstorm and tell me what you see. Hopefully you enjoyed today. Thanks for your time, and I'll talk to you again soon.